confidence intervals in R. Let's see. First, we'll deal with one sample data. CI for mean with known variance, when our variance is known. So there's no built-in function for that in R because it doesn't occur in real life. We'll do it by the scratch method. Okay, so let's see this question. Average IQ of a sample of 50 university students was found to be 132. Calculate a 95% symmetrical confidence interval for the population. The average IQ, assuming that the IQs are normally distributed, and it is known from the previous studies that the SD of the IQs is approximately 20. What do we know? We know N is 50. We know the average X bar is 132 and the SD is 20. What is the test statistic for this? The test statistic for this is X bar minus mu by sigma by root n. This is the CS1 material which I'll be following, and we'll do questions also from here only. So it is X bar minus mu by sigma by root n, where sigma is known to us. It follows normal 0, 1. So the interval becomes something like this: X bar plus minus 1.96 into sigma by root n, and this 1.96 is dependent on the 95% confidence interval. This can vary. When we have 90% confidence interval, this will change. Okay, so let's do this in R. We have N equals to 50. N is equal to 50. Then we have X bar is 132. X bar is 132. Then sigma is 20, the SD. And then I have alpha, which is 0.05, because I have to construct a 95% confidence interval. Okay, so alpha is 0.05. Alpha is 0.05. Then we have to construct a confidence interval. What is a confidence interval? It is X bar plus 1.96 into sigma by root n, that is SQRT of n. One way is this is the first, and the other one will be X bar minus 1.96 into sigma by root n. Okay, so these are two ways of calculating. We can actually get these together only. How we will get this together? X bar plus C into C of minus 1, 1. If I write minus 1 and 1 together into, this is 1.96. How can I get 1.96? We can use Q norm. We can use Q norm of what? 1 minus, our alpha is 0.05. So 1 minus alpha by 2. Okay, we can use Q norm of 1 minus alpha by 2. Into sigma by SQRT of n. And this is the way. And see, if I run this, I get the same confidence intervals. If you all are thinking, what does this give? See, 1 minus alpha by 2 is 0.975, and Q norm of 1 minus alpha by 2 is 1.9599, that is 1.96, which we use here. Okay, this is called the scratch method. That is basically following the theoretical formula. Okay, next, it is CI for mean with unknown variance. When I have mean with unknown variance, calculate a 95% confidence interval for the average height of 10-year-old children, assuming that heights have normal distribution based on a random sample of 5 children whose heights are 124, 122, 130, 125 and 132. So first let's store our data. First we'll store our data. So C of 124, 122, 130, 125 and 132. This is the data. Then I need to find my x bar, which is mean of data. I need the SD or sigma, which is SD of data, because here is the sample standard deviation. We do not know the SD. Then I have N. N is the length of data. N is length of data. This is 5. And then alpha is again 0.05. So what is the test statistic here? The test statistic here is x bar minus mu by s by root n follows Tn minus 1. It follows a T distribution, and here our S is the sample variance, because sigma was, earlier the sigma was known, the standard deviation was known. Here it is unknown. Sigma is unknown, so it follows T distribution. So first on the scratch method we can calculate Ci, we know as seen above. So let's write x bar plus C of minus 1 comma 1 into Qt, because it's T distribution we'll use Qt, and then again 1 minus alpha by 2 into, here it's SD now, SD by SQRT of N. Okay, we did not specify the DF. In Qt we need to specify the DF. So what is, it is Tn minus 1. So our degrees of freedom is n minus 1. So this is the confidence interval, 121.3614 and 131.8386. This was scratch method. But for T test, for T distribution, for this statistic, we have an inbuilt test in R also. Here we did not have any inbuilt, nothing was there, because it doesn't use in real life, but here it is there. Using T dot test. So using T dot test we get, see the syntax is T dot test, data, and then my confidence interval for which I need the value. T dot test, confidence interval, and data for which I need the value. So here T dot test I use, my data is stored in data, my data, the heights are stored in the vector data, so I will write data here, and confidence level how much I want, it is 95% confidence level, so I write conf equals to 0.95. Can you see? All these are given. T equals to this is a test statistic, DF is degrees of freedom 4, which is show n minus 1, 5 minus 1 is 4, p value is given, alternative hypothesis, true mean is not equal to 0, and then we have the 95% confidence interval, 95% confidence interval, and sample estimates mean of x. So many data is given. If we want only the confidence interval, what we do, store this in value, say test, any name you can give. I've stored this in test, and then if I write test $conf, test $conf, I will get only the confidence interval. I will get only the confidence interval. Okay, so this is how this, see, you can see it's original, we got from the scratch method also, we got these values only, and from t test also we are getting these values. Okay, Next, moving on to CI for variance. CI for variance. Again, for variance there is no built-in function, so we have to do it from scratch. Okay, for variance also there is no built-in function. Calculate a 95% confidence interval for the variance of height of 10-year-old children, assuming that heights have normal distribution based on a random sample of 5 children whose heights are 124, 122, 130, 125 and 132. So data remains same here, but we have to now test the 95% confidence interval for the variance. So let's see what is the test statistic here. So it is this. The 95% confidence interval for variance is n minus 1 sigma s square by, again it's s square, the 95% confidence interval. Let's see the test statistic first. The test statistic is n minus 1 into s square divided by sigma square follows chi square n minus 1. Okay, where s is the sample variance, sigma is the population variance. Okay, and what is the confidence interval? It is n minus 1 s square by chi square 0.025 comma n minus 1 and n minus 1 s square chi square 0.975 comma n minus 1. Okay, so let's do this in R. Data remains the same for heights, so let us store it once again. It's remaining the same. N is again length of data. It gives us a count of the data. I have alpha equals to 0.05, and then the confidence interval is, say I'm using C so that both the confidence intervals get displayed together. It is n minus 1 into s square, that is n minus 1 is sample variance. How do we get my sample variance? var of data, that is sample variance divided by chi square distribution q chi sq into 1 minus alpha by 2, 1 minus alpha by 2, and degrees of freedom is equal to n minus 1, df equals to n minus 1. This was one, and the other one is n minus 1 into variance of data divided by q chi sq alpha by 2 comma n minus 1. And if I run this, so we have, oh, there's an extra comma here, or extra slash, alpha by 2. So this is my CI 6.38 and 146.98. Okay. Next, moving on, we have CI for P using binom dot test. CI for P exact. Okay. So what is the question? It said we have obtained a value of 1 from binomial 20 comma P distribution. Construct a 95% symmetrical confidence interval for P. So I already told you we'll use binom dot test. So let's see. First, x is given to us as 1. The value of 1 is obtained. Okay. N is 20. N is 20. How is binom dot test syntax looks like? Binom dot test, it is first x, then we need to specify n, and then our confidence interval, and then the confidence interval. This is the syntax. So for this case, we'll use binom dot test. Binom dot test 1, our x value which is stored in 1, n, and confidence interval is equal to 0.95. We need a 95% confidence interval. So I can see exact binomial test, and this is a 95% confidence interval. Same way we can pull the values from binom dot test. If I store this in test, so test $conf will give me the 95% confidence interval. Okay. Next, CI for P for normal approximation, CI for P with normal approximation and exact binom dot test. We'll use both. So it's in a 1-year mortality investigation, 45 of the 250 90-year-old present at the start of the investigation died before the end of the year. Calculate a symmetrical 90% confidence interval for the probability of death. So first let's see what is the statistic for this binomial distribution. So it is something like this: theta cap plus minus 1.96, that is z alpha by 2 whatever, and root over theta cap into 1 minus theta cap by n, where theta cap is nothing but x by n. Theta cap is nothing but x by n. So it's in a 1-year mortality investigation. Same question we are dealing with now. Let's see. And x is 45, n is 250, n is 250, p hat is x by n as we saw. Here alpha becomes now what? Since I have a 90% confidence interval, alpha becomes 0.1, and then my CI comes. CI is p hat plus c into minus 1 comma 1 into q norm 1 minus alpha by 2 into sqrt of what is there, p hat into 1 minus p hat divided by n. So sqrt of p hat into 1 minus p hat whole divided by n. Okay, so this is the confidence interval. Okay, this was by normal approximation. We can also use the exact binom dot test. So binom dot test x n and confidence interval equals to 90%. So conf equals to 0.9. See, 0.1014033 and here 0.141 and 0.224. This is approximated and this is exact. This is an approximated normal approximation. This is exact binomial distribution test. Okay. Extracting values I showed you. Again, same way you can extract. Next, moving on. CI for lambda, you exact using Poisson Dot Test. So we have obtained the value of 1 from Poisson L distribution. This is L. Construct a 90% symmetrical confidence interval for lambda. So I need to construct a symmetrical 95% or 90%. So here also x is 1 initially. Let's see the syntax of Poisson Dot Test. It's Poisson Dot Test. First we specify x, then we specify t, then we give t, and then we give the confidence level. Now what is T? X is the number of events which you have done. T is the base time events, time base for the event that has occurred. Here how many times you have done the event? It is only once. We have done only once. So T is the time base for the events which has occurred. Okay. Default is always 1. Default is always 1 for T. So here it is Poisson dot test. Poisson dot test. X value is 1. T is nothing, so we will assume it's 1. So we don't have to write it because default is 1. And then confidence interval equals to 90%. So conf equals to 0.9. So I get the exact Poisson test. This is the 90% confidence interval. Okay. Let's do a next question. In CI for lambda with normal approximation and exact Poisson dot test. So again, in 1 year investigation of claim frequencies for a particular category of motorists, the total number of claims made under 5,000 policies was 800. Assuming that the number of claims made by individual motorists has Poisson R distribution, calculate a 90% CI for the unknown average claim rate R. So again here my X is 800, N is 5,000, T is 5,000, and we have to obtain a 90% confidence interval. So first let's use normal approximation. Again let's see the statistic for normal approximation. For Poisson, it is x bar plus minus 1.96 into root over x bar by n, or maybe we can see this x bar minus lambda by root over of lambda by n. Okay, see same sum we will deal with now. So it is x bar minus lambda root over lambda by n follows normal 0, 1. Okay, so let's do x for x is 800, n is 5,000, lambda hat is again x by n, lambda hat is also x by n, alpha is again 0.1 because we need a 90%, 0.1, and by normal approximation it becomes L hat plus C of minus 1, 1 into Q norm 1 minus alpha by 2 into SQRT of L hat by M. Okay, so this is my confidence interval 0.1506953 and 0.169. We can use the Poisson dot test also directly. So Poisson dot test, it is x comma n, t is the time base n 5,000 times, and confidence level is equals to 0.9. Unexpected symbol. Okay, I forgot to give a comma. So this is a 90% confidence interval. Same way we can extract value of confidence interval for Poisson dot test also. I am every time giving test name, you can give any name over here. So 0.150814 and 0.16968. Again there is a difference between these two because this one is approximated normal approximation, this is exact Poisson test. Okay, that's it. This is what this was for one sample data. Okay.